Hello guys, welcome back to my channel Algorithm Avenue. In our previous video, we have discussed about the ReLU activation function in detail. Okay, basically this ReLU activation function is used in the hidden layers to find out the complex nonlinear patterns in the dataset. Okay, now when I use an activation function in the hidden layers, it must not possess any single problem. Okay, but this ReLU activation function possesses a major problem, that is dyingreluproblem. Okay, now in this video, our aim is to understand in detail about dyingreluproblem and also discuss the various variants that came into existence to solve this dyingreluproblem. Okay, now let's basically see what actually this dyingreluproblem is. Okay, now this is my sample neural network. Okay, I'm using ReLU activation function in this sample neural network. Okay, now I'm considering this node. Okay, now I'm considering this node. Now let's say this node is dead by using ReLU activation function. Okay, by using the ReLU activation function, this node in the hidden layer is dead. Okay, now what actually this dyingreluproblem specifies, by using a ReLU activation function in the hidden layers, there are chances that neurons may be dead. Okay, if once the neurons are dead, they are dead forever and are not used in the training process. Okay, now let's say this neuron is dead. Okay, now when this neuron is dead, it is dead forever, and in the entire training process, okay, in the entire forward propagation and backward propagation in each epoch, this hidden unit is not at all used. Okay, this is basically dyingreluproblem. Okay, now we'll be discussing in detail how these neurons are dead in the further part of the video. But before that, I need to specify a thing that in an artificial neural network, 50 if more than 50% of the neurons are dead, then the predictions of the artificial neural network are not accurate. Okay, when the 50% more than 50% of the neurons are dead, then the predictions of the artificial neural network are not accurate. Okay, now there are also chances that 100% of the neurons may be dead. Okay, there are also few chances that 100% of my hidden units, okay, hidden neurons may be also dead. Okay, now when 100% of the hidden units are dead, then there is no persistence of the neural network. Okay, there is no existence of the neural network. Okay, when there is no existence of the neural network, then the entire training process does not happen, right? Now let us basically see how these neurons are dead. Okay, how actually these neurons are dead and how this dyingreluproblem actually occurs. Okay, now let's say this is my sample neural network and I'll be talking with respect to this node. Okay, I'll be entirely discussing with respect to this node. Okay, now with respect to this node, when I calculate weighted some value, that is z1 is equal to x1 w1 plus x2 w2 plus b1, right? Now in this hidden layer, okay, in this hidden layer I'm using ReLU activation function. Okay, what is the formula of ReLU activation function? A1 is equal to, okay, I'll write it with uppercase letter. A1 is equal to max of 0 comma z1. Okay, a1 is equal to maximum of 0 comma z1. Okay, when z1, okay, z1 weighted some value is positive, the output will be z1. Okay, output of ReLU activation function will be z1. When z1 value is negative, then activation function output will be 0. Okay, when z1 is positive, the activation function output will be z1, and when z1 is negative, the activation function output will be 0. Okay, now let's say, okay, let's assume that z1 is less than 0. Okay, z1 is negative value. Okay, when z1 is negative value, maximum of 0 comma negative value will be 0, right? So a1 becomes 0. Okay, a1 becomes 0. So when I try to find the derivative with respect to z1, it will also be 0. Okay, if I differentiate this 0 value with any parameter, it will be 0, right? So dou a1 by dou z1 is equal to 0. Okay, now what actually happens due to this 0 numerical value is, when I try to update the weights and bias value, they won't be updated. Okay, Now let me write the formula for weight updation. This is equal to W old minus learning rate dou L by dou W1. Okay, now when this value is 0, this entire gradient value becomes 0. Okay, when this value becomes 0, this entire gradient value becomes 0. So when I multiply 0 with learning rate, this entire term, okay, this entire term becomes 0. Okay, when this entire term becomes 0, W new will be is equal to W old. Okay, the new weight value will be equal to old weight value. Okay, when new weight value is equal to old weight value, there is no weight updated. Okay, there is no weight updated, and this continues forever. Okay, this continues until the entire epochs are completed. So in the entire neural network, the weights you have initialized at the beginning will persist till the entire training. Okay, till the entire training, same weights will be, okay, same weights will be continued, and there will be no updation of the weights. So it will not be able to, so neural network won't be able to learn complex patterns in the data set. Okay, this is the entire dying-ReLU problem. Now let's mathematically prove how this value, okay, how this gradient value will be 0. In our previous section of the video, we have seen that the gradient value being 0, and due to this gradient value being 0, the weights and bias are not being updated. Now let us see the mathematics behind why actually this gradient value is becoming 0. Okay, now I'm considering the same neural network, and I'll be talking with respect to this node. Okay, remember, I'll be talking with respect to this node. Okay, this is the entire chain rule with respect to this neural network. Okay, now the loss of this neural network is represented by L. L is dependent on y hat, that is the predicted output. Now my y hat is dependent on three parameters, that is W3, B2 and A1. A1 is the activation output of this node. Okay, now A1 is dependent on Z1. Okay, A1 is directly dependent on Z1, that is the weighted sum value of this node, and Z1 is directly dependent on five parameters, that is W1, W2, X1, X2 and B1 bias. Okay, now let us write the weights and weights updation formula. Okay, now I'm considering this node, right? So I'll be writing with respect to W1 and W2, and I'll be ignore this W3. Okay, now W1 new is equal to W1 old minus learning rate dou L by dou W1 old. Okay, now W2 new is equal to W2 old minus learning rate dou L by dou W2 old. Right, now I said that this value is 0. Okay, these two gradient values are zeros. Now let us see why, how actually these gradient values are being 0. Okay, now I'll be writing the same over here, dou L by dou W1. This is equal to, now let's follow the chain rule. Okay, now loss is dependent on y hat. Okay, and y hat is dependent on, directly dependent on A1, and A1 is dependent on Z1, and Z1 is dependent on W1. Okay, this is the chain with respect to W1. Okay, this is the chain with respect to W1. Now let us write the same content over here, dou L by dou y hat multiplied by dou y hat by dou A1 multiplied by dou A1 divided by dou Z1 multiplied by dou Z1 divided by dou W1. Okay, this is the entire expansion of this gradient value. Okay, now let us consider this part. Okay, only this single term. Okay, now when I apply ReLU activation function to this node, and when my z value, okay, when my z value is negative, then the activation function output will be 0. Okay, when my activation function output is 0, then dou A1 by dou Z1 is 0, right? This implies dou A1 by dou Z1 will be 0. Okay, when my z value is negative and when I pass through the ReLU activation function, then A1 becomes 0. Okay, activation function output becomes 0. When I write the derivative with respect to Z1, the derivative value will be also 0. Okay, now I am substituting the same value over here. Okay, now when this term is 0, now when I multiplied 0 with this entire three terms, they become 0. Okay, this entire value becomes 0. Okay, means dou L by dou W1 will be 0. Similarly with respect to dou L by dou W2 as well. Okay, now when I consider dou L by dou W2, this will be my path. Okay, excluding this W1, this entire thing will be my path. Okay, now similarly when I write this expansion over here, I'll be getting here dou a1 by dou z1. Sorry, dou a1 by dou z1. Okay, now similarly dou a1 by dou z1 will be also equal to 0. Okay, dou a1 by dou z1 will be also equal to 0, and when I multiply 0 with respect to this terms, okay, with this terms, this entire gradient value will be equal to 0. Okay, now when this the gradient values are equal to 0, now when I multiply this gradient values over here with respect to learning rate, this entire term becomes 0. Okay, this entire terms becomes 0, and W1 new will be equal to W1 old, and W2 new old new will be equal to W2 old. Okay, now when my new weight values are equal to old weight values, then there's no weight being updated. Okay, when there's no weight being updated, then there is no training process. Okay, there is no training process involved. Okay, when there is no training, then there is no prediction. Okay, there is no proper prediction. Okay, this is how the gradient value is being 0, and due to this gradient value being 0, we'll be facing the dying ReLU problem. Okay, now let us discuss why actually this z values will be 0. Okay, how the z values will be 0. Okay, now the z values are 0 in two cases. Okay, the z values will be 0 in two cases. There are two cases. Okay, now in first case, okay, in first case, okay, high learning rate. When we set learning rate to higher, then the okay, I'll be explaining with respect to an example so that it will be much clear. Now when I write z1, okay, z1 is equal to x1 w1 plus x2 w2 plus b1, right? Okay, this is the value of z1. Okay, now when you keenly observe, these are my weight values. Okay, these are my weight values, and I'm updating this weight values over here. Okay, I'm updating this weight values over here. Now when I set my learning rate to higher, sorry, now when I set my learning rate to higher, that may be 2, 3, 4, 5, 6, any higher numerical value, then what actually happens is this value, okay, this term, you see this term will be greater. Okay, this term, okay, this term will be greater than this w1 old value. Okay, learning rate into dou l by dou w1 old will be greater than, okay, will be greater than w1 old. Okay, when this value is greater than this w1 old, then w1 new will be an negative value, right? When this value is greater than this value, as you are performing subtraction, this w1 new value will be negative. Okay, now similarly with respect to w2 new as well. Okay, now when you set the learning rate as higher, this entire term, okay, this entire term will be greater than w2 old. When this entire term is greater than w2 old, as you are performing subtraction, this will be also negative. Okay, now this both values are negative. Okay, this value is negative and this value is negative. Now when you multiply this negative value with respect to x1, this will be negative and this will be negative. Now when you add both these negative values, that will be much greater negative value. Now in case, okay, I'm specifying that in case if this negative values are greater than this bias, okay, when this negative values are greater than this bias, then z1 value will be less than 0. Okay, when this both these terms, okay, when you add when you add both these terms, we'll be getting a resultant numerical value which is negative. Okay, when this negative value will be greater than this bias, okay, when this negative value will be greater than this bias, then z1 value will be negative. Okay, this is our first case. Now in the second case, we have high negative bias. High negative bias. Okay, what actually happens in this high negative bias is when you keenly observe this formula, our Z1 value is extremely dependent on three parameters: W1, W2, and B1. Right? This X1 and X2 are true values. Okay, they are from the data, we cannot alter them. So only values that we can alter is W1, W2, and V1, right? Now, let's say W1 value is positive and W2 value is positive. Okay. Now, when we multiply this both these values, this will be positive and this will be positive. When I add, it will be a positive numerical value. Now, when I set B1 to higher negative value, okay, higher negative value, when both this when the resultant value, okay, resultant numerical value, that is positive value, is less than this bias. Okay, when this resultant numerical value, that is positive numerical value, is less than this bias, then we'll be getting Z value as negative. Okay, Z value as negative. Okay, this happens in two cases. Okay, higher negative bias happens in two cases. First is, you might have by mistakenly set the value to an higher negative value. Okay, bias value to an higher negative value, or you are updating the way, okay, sorry, you are updating the bias with the same process as you are updating the weights. Okay, now you are setting a higher higher learning rate for the bias as well. Okay, you are setting the higher learning rate for the bias as well, and you are doing the same updation formula for the bias. Okay, so the bias becomes negative value and much negative value and much negative value. So due to this, Z1 value will be negative. Okay, this high negative bias happens in two cases. First is, either you by mistakenly set the value to higher negative value, or you are updating the bias value similar to the weights as well. Okay, now if my learning rate is higher, okay, if my learning rate is higher and you're updating the bias, then this bias value will be negative, and similarly as you go on updating, it becomes much negative value. So in this case, Z1 will be negative. Okay, these are the two cases where we'll be having higher negative bias. Now in the next section of the video, we'll be discussing the possible solutions to avoid this dying ReLU problem. Now, let us discuss all the possible solutions to overcome this dying ReLU problem. Okay, among them, the first is reasonable learning rate. Okay, in cases where we have set the learning rate to higher, we have seen that the weights value getting negative, and when weights values are negative, then the Z value is being negative. Okay, so that is why we need to set a reasonable learning rate. Okay, the second possible solution is reasonable bias. Okay, now, when we have chosen a higher negative value for the bias, then Z value is being negative. So, to prevent this, we need to choose a reasonable bias. Okay, okay, reasonable bias is nothing but 0.01. Experimentally, the best bias value has been proven as 0.001. Okay, the third possible solution is using the variance of ReLU. Okay, different variants of ReLU has been introduced to solve this dying ReLU problem. Okay, now this variants of ReLU are classified into two types. Okay, one is linear and second is non-linear. Okay, this linear variants are nothing but they are obtained by applying linear transformations on ReLU activation function. This non-linear are obtained by applying the non-linear transformations on the ReLU activation function. Okay, in linear, the first activation function is Leaky ReLU. Okay, Leaky ReLU. The second activation function is PReLU. Okay, parametric ReLU. Okay, PReLU is nothing but parametric ReLU. Okay, now in non-linear activation functions, the first one is LU. Okay, exponential linear unit, and the fourth activation function is SELU. Okay, scaled exponential linear unit. Okay, these are the four possible variants of ReLU to solve this dying ReLU problem. Okay, now let us discuss each of these activation functions in detail. Now let us discuss different variants of ReLU activation function in detail. Okay, among them the first activation function is Leaky ReLU. Okay, this is the graph of Leaky ReLU activation function. It is same as ReLU activation function, but on the negative side, okay, on the negative side there exists the value of the activation function. Okay, in ReLU activation function, when the z value is negative, the output of the ReLU activation function is 0. Okay, but whereas in leaky ReLU, when the z value is negative, the output of ReLU activation function is 0.01 into z. Okay, 0.01 into z. Okay, finally, the leaky ReLU activation function can be written as maximum of 0.01 into z comma z. Okay, for the positive z, it is same as the ReLU activation function, but for the negative z, it is 0.01 into z. Okay, this is the basic difference between leaky ReLU and ReLU activation function. Okay, in ReLU activation function, for the negative z, the output is 0, but in leaky ReLU, for the negative z, output is some numerical value. Okay, there exists an output when the value of z is negative. Okay, now let us see the advantages of leaky ReLU activation function. Okay, the first advantage is non-saturating. Okay, the ReLU activation function is non-saturating for positive region, but whereas in leaky ReLU there exists a value at the negative side of the z, so it is non-saturating for the positive and negative as well. Okay, for positive it is a non-saturating, and for negative as well it is non-saturating. Okay, and second is easily computed. Okay, the calculation of derivative for this is easier, so it is easily computed. Okay, third is no dyingreluproblem. Okay, as there is exist value for the negative region. Okay, as there exists a value for negative z, so there is no dyingreluproblem. Okay, fourth is close to zero center. Okay, now when z values are negative, okay, let's say when z values are negative, they will be multiplied with this. Okay, they will be multiplied with 0.001, but in the previous ReLU activation function, when z values are negative, it is 0, but when the z values are negative, in this leaky ReLU activation function, we get a negative value as output. Okay, but previous ReLU activation function, we get only positive values or 0, but here the activation function output will may be negative, may be positive. Okay, maybe negative, it may be positive, so it is close to zero centered. Okay, why we are calling it as close? Because we are multiplying with a smaller numerical value, that is 0.01. So the negative value, we get negative values, but they are close to zero. Okay, they are close to zero, that is smaller numerical values, so we call it as close to zero center. Okay, now the second activation function is parametric ReLU. Okay, the only basic difference between leaky ReLU and parametric ReLU is here, instead of a numerical value 0.01, we have an parameter. Okay, we have a parameter A. Okay, this A is a trainable parameter which gets updated at each epoch. Okay, it gets updated same as the weights at each epoch. Okay, so the activation function of parametric ReLU is maximum of az comma z. Okay, maximum of az comma z, but whereas in leaky ReLU it is 0.01 into z, but here we have az. Okay, a is an trainable parameter. Okay, it's a trainable parameter, it gets updated based on the data and each epoch of the training. Okay, trainable parameter. Okay, the only advantages between the leaky ReLU and parametric ReLU is it is parameter dependent. Okay, the value of this value, okay, this negative side value is parameter dependent, but whereas in leaky ReLU, here we have fixed numerical value. Okay, this is the only difference between leaky ReLU and parametric ReLU. Now let us discuss the rest of the two activation functions in detail. Okay, among them the first is LU activation function, that is exponential linear unit activation function. Okay, this is the graph of LU activation function. It behaves same as ReLU activation function when z value is positive, and when z value is negative, this is the formula. Okay, LU of x is equal to x if x is greater than 0, and for negative value of x, the formula is alpha into e power x minus 1 if x is less than or equal to 0. Okay, this is basically LU activation function. Okay, you might have a doubt that what is this value of alpha. Okay, generally the value of alpha ranges from 0.1 to 0.3. Okay, the value of alpha ranges from 0.1 to 0.3. Okay, this is the graph. Okay, this is the graph of the negative side when alpha is equal to 0.1. Okay, when you further increase this value of alpha, the graph changes in this way. Okay, and when you further increase this graph value of alpha to 0.3, the graph changes in this way. Okay, this is how the changes are done in graph based on the value of alpha. Okay, this alpha is an hyperparameter. Okay, this alpha is an hyperparameter. Okay, this is the derivative of LU activation function. 1 for greater than 0, and for less than 0 it is LU of x plus alpha. Okay, now let us discuss the advantages and disadvantages of LU activation function. Okay, the first advantage is it is close to zero centered. Why we are calling it as close? Because it is multiplied with smaller numerical value, so we call it as close to zero centered. Okay, second is better generalization. Okay, this LU activation function performs well on the test data. Okay, the third is no dying ReLU problem. Okay, there is no dying ReLU problem as there exists positive values as well as negative values. Okay, fourth is differentiable. Okay, when you see the graph of LU activation function, it is an continuous graph. Okay, it is an continuous graph, so it is differentiable at any point, so we call it as this is the fourth advantage of LU activation function. Okay, now let us discuss fourth activation function, that is SELU activation function. Okay, scaled exponential linear unit. Okay, that is meant by SELU. Okay, now there is only a small difference between SELU and LU activation function, that is here we multiply an extra parameter, that is lambda. Okay, only the extra parameter lambda is multiplied in case of SELU, but in case of LU activation function it is just multiplied with alpha, a single parameter. Here we multiplied by another extra parameter, that is lambda. Okay, now you might have a doubt that what are these values of alpha and lambda. Okay, this values of alpha and lambda are two constants. Okay, I'll be displaying the values over here, you can check them out. Okay, this alpha and lambda are constant values. Okay, they are fixed constants. Okay, alpha and lambda are not trainable parameters, they are fixed constants. Okay, this is the derivative value of SELU activation function, that is lambda multiplied by 1 into lambda into 1 if x is greater than 0, lambda times alpha into e power x if x is less than or equal to 0. Okay, there is one major advantage with this SELU activation function, that is, let's consider an hidden layer. Okay, let's say this is an hidden layer. Now when you apply SELU activation function to this hidden layer, the output, okay, the output of each of this node, okay, each of the hidden unit mean is equal to 0. Okay, the mean of all this, okay, the mean of all this activation function outputs of this hidden layer is 0 and standard deviation is equal to 1. Okay, the mean of this hidden layer, okay, the mean of this hidden layer is equal to 0 and standard deviation is equal to 1. That means SELU activation function is self-normalizing. Okay, when SELU activation function is self-normalizing, then there will be better generalization in case of SELU activation function and training becomes faster. Okay, this is all about LU and SELU activation functions. Okay, now let us see how do we actually implement this SELU and ReLU activation functions and rest of the two activation functions on a dataset.
Now I'll be considering make circles dataset and implement all the 4 activation functions on the dataset. Okay, for that I'm implementing the necessary library. This is my and this is circles dataset, and I'm considering train test split library to split my data to 80% to training and 20% to testing, and I'm converting from NumPy to tensors, and after that I'm building my model with Leaky ReLU activation function. Okay, this is my model with Leaky ReLU activation function. Okay, in place of ReLU just we need to replace as Leaky ReLU. Okay, now this is my model with Leaky ReLU activation function, and this is my loss function and optimizer. This is my entire training loop and this is my testing loop. Okay, these are the model results. The training accuracy is around 84.25 and test accuracy is around 84%. Okay, this is my model decision boundary. Okay, after that I'm implementing Parametric ReLU activation function. Okay, in place of Leaky ReLU just I'm replacing PReLU. Okay, this is the model with Parametric ReLU activation function, and these are my model results, that is training accuracy is around 85.38 and test accuracy is around 84.50. Okay, this is similarly my decision boundary. Okay, after that I'm implementing ReLU activation function, okay, exponential linear unit, okay. Just in place of PReLU, you need to write ReLU activation function. I'm considering alpha value is equal to 1. This in place value is by default false, so I'll not change it. So I choose default as false, okay. Similarly, in my second layer, I'm implementing ReLU activation function, okay. Now my model results are at 90th epoch I got around 84.38 and test accuracy to be 83%, okay. Now I am choosing SELU activation function. In place of ReLU activation function, you need to write SELU, okay. This is my model with SELU activation function, okay. Now I am running the entire training process, and at the 100th epoch I got around 84.50 and test accuracy is around 83.50, okay. This is the implementation of all the 5 activation functions including the ReLU activation function on the make circles dataset, okay. There will be a slight change in the model results, that is 1 to 2% change in the accuracies, but mostly the results will be similar, okay. You'll be finding only the changes when the datasets are larger or you choose a larger model for training, okay. This is the entire video on activation functions, okay. Hope you like this video. If you like the video, please like, share and subscribe.